So it's Fun Fact Friday. In this video, I want to look at a paradox that we get with improper integrals. It's sometimes called Gabriel's horn, sometimes called the painter's paradox. So this involves improper integrals, so let's review how those work. So if I want the integral from 1 to infinity of 1 over x dx, what does that mean? That means the area under the curve 1 over x from 1 off to infinity. Okay, so the way mathematicians define this is to say, well, I'm going to treat this as a limit of some dummy variable, I'm going to call it t, going to infinity, and look at the area from 1 to t. So I'm going to look at the area from 1 to a million, 1 to a billion, 1 to a trillion, and see if those values close in on a number. Okay. In this case, with 1 over x, let's see, an antiderivative of 1 over x is natural log of x. And the fundamental theorem says I can then plug in my endpoints. Notice here I needed a number t to use the fundamental theorem. So we have the limit as t goes to infinity of the natural log of t minus the natural log of 1, which is just 0. So we can actually ignore that, minus 0. Okay, but this, as t goes to infinity, the natural log function does go to infinity. So we say this improper integral diverges. If we'd gotten a number, it would converge to whatever that number is. All right, so that's the idea we're going to use for Gabriel's horn. But we're going to get more complicated here. Instead of just the area under the curve, I'm going to create a 3D shape and look at its volume and its surface area. So I'm going to take this function, this 1 over x function, and spin it around the x-axis. So that means it's going to come out of your screen and then go back behind your screen. Okay? So this is making a 3D shape, kind of like a horn that never ends because it's going off to infinity. All right, so think of it as a hollow tube that curves at the end and ends here at 1. So that's what we have. We have this hollow tube heading off to infinity, and the end of it is squeezing down, squeezing down, squeezing down, but it's still a hollow tube. That's what we're going to look at. All right, so first thing I want to look at for this tube is the volume. So if you haven't seen the disk and washer method for solids of revolution, we can get a basics of it here to understand what's going on. So this entire tube I can think of as circles the whole way across, right? Every cross section is a circle, circle, circle. And I have circles going from 1 to infinity. So my volume is going to be adding up the area of those circles from 1 to infinity. But what's the area of a circle? It's pi r squared. So I just need to figure out the radius for each circle. Well, look, the radius for my first circle is the function value at 1. The radius for the circle at 4 is the function value at 4. The radius for this circle is the function value at that point. So my radius is always the function value. So we're looking at the integral 1 to infinity pi of my function, which is 1 over x squared dx. Okay, here we go. Let's calculate this. So I have the limit as t goes to infinity, integral from 1 to t of pi times x to the negative 2. Antiderivative of x to the negative 2 is going to be negative 1 over x. You can work that out. okay, if you need to see the details, but that is what I'm going to plug my endpoints into. So we have the limit as t goes to infinity of pi times my antiderivative with t plugged in minus my antiderivative with 1 plugged in. Okay, but t is going to infinity, so that means 1 over t is going to 0. So my limit, I'm going to have pi times 1, which is just pi. So what we've shown here is the volume of this infinite hollow tube is pi. Okay, so the volume is pi. Now let's look at the surface area. So for the surface area, I need to think about if I take a little hollow segment here, and I want to think about the surface area going around that little segment. So you may or may not remember your formula for things like that from geometry. I'm still going from 1 to infinity, but I have 2 pi r times the length of that line there. Okay, so the length of that line there. Well, the length of an arc like that is going to be the square root 1 plus the function's derivative squared. Okay, that's the arc length for a function of x. So I'm going to need that. So we're going to need the square root 1 plus the function's derivative squared dx. Okay, but I know my radius. My radius, we said, is always going to be my function value. That's going to tell me how big the radius of my circle is. So that's 1 over x. And the derivative of 1 over x is negative 1 over x squared. So here we go. We're going to need to do some algebra. All right. And I'm not even going to write the limit part in. Okay. We're going to leave this as 1 to infinity. 2 pi 1 over x, the square root. Now I'm going to leave some of the algebra for you to work out. But if you square out that negative 1 over x squared and then find common denominator with the 1 and everything, you will get x to the 4th plus 1 over x to the 4th. Okay, so that's just algebra, getting from that first integral to this second one. Now, here's what we're going to do, because technically we don't know how to evaluate this integral as is. Even if I rewrite it as limit as t goes to infinity, I'm still going to be stuck. But I notice if I didn't have that plus 1, this would simplify down really nicely. Okay. And as I go to infinity, x is things like a million, billion, trillion, that plus 1 is not going to make much difference. So let's think about this without the plus 1. So what I'm going to think about here, let me switch colors, is the integral from 1 to infinity of 1 over x. So let me write in my original, x to the 4th plus 1 over x to the 4th. I'm going to think about how that compares to if I get rid of the plus 1. Well, if I get rid of the plus 1, this whole term is just going to become a square root of 1, right? If we get rid of the plus 1, x to the 4th over x to the 4th is 1, which will be square root of 1, which will be 1. So I'm going to have the integral from 1 to infinity of 1 over x dx. Okay. If I'm getting rid of the plus 1, I made this whole fraction smaller. Not by much, but a tiny bit smaller. So that means my original integral, because it has the plus 1 in it, is bigger than the simplified when I get rid of the plus 1. Okay? But wait, we already know something about this integral. That's that very first integral we did. We know that this heads off to infinity, that it diverges. That means if this integral is even bigger, it has to go to infinity. It can't stop at a number because it's bigger than something that already went off to infinity. So it diverges. So here's our paradox. My surface area, I guess I should write that's what this is infinite. That means if you give me infinitely many cans of paint, all right, I still would never be able to finish painting the outside of this hollow tube of this horn. But my volume was finite, so I could fill it with paint, but I could never paint it. And that's the paradox of Gabriel's horn.